Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 63, and it is entitled Prisms and Total Internal Reflection. Lens aberrations are also included by your authors in this lesson, but we will not take it up because it doesn't appear on the AP exam. However, if you are building precision optical devices such as cameras or telescopes, it's an important topic, and it has to do with dispersion. Most of you will recognize this image. It's of the record cover of Pink Floyd's best-selling album, Dark Side of the Moon. Aren't your eyes just drawn to the colors dispersed by the prism? White light comes in from one side, and colored light emerges from the other side. How that happens is part of today's subject. Dispersion also happens in rainbows. Everybody's seen a rainbow outside on a rainy day, but rainbows aren't visible every single time there's rain. All of the conditions have to be exactly right for you to be able to see it. Why do those colors always appear in the same order? Red on the outside of the arc, violet on the inside. Or maybe you've flown in an airplane and looked out the window to see a full circle rainbow around the shadow of the plane. Why can't you see a complete rainbow circle from the ground? And who can't appreciate the dispersion produced by gems such as diamonds? For many couples, the gift of one of these precious gems set in a ring serves as a tangible symbol of their commitment to each other. The flash of color produced by light interacting with diamonds is easily understood if you can come to grips with colors in rainbows. So, in this lesson we take up the topic of dispersion, or the spreading of light into different frequencies when it passes through a material, such as glass or water or diamonds. We'll also bring up the topic of total internal reflection, which accounts for some interesting natural phenomenon and has many important technical applications in the telecommunication industry. Let's start with total internal reflection first, and then we'll mix in dispersion. Let's begin with a numerical problem. You're going to need a pencil and a paper and your calculator for this, and you ought to follow along and do this as we do it together. Let's suppose that I take a ray of light that's incident from beneath the surface of water onto a boundary with air. You could imagine a diver with a laser pointer below the water shining it upward. Why he has a laser pointer down there, I don't know, but that's what he's doing, and so let's calculate. Let's suppose the angle of incidence is 50 degrees. If the index of refraction of water is 1.33, I want you to calculate the angle at which the light emerges into the air. So pause the recording now and give it a try. Have you got an answer yet? If you haven't gotten your pencil out, shame on you. You should be doing this. Have you gotten a number yet? If you didn't give it a try, you're robbing yourself of an important learning opportunity. Take out your pencil and paper and calculator and give it a go. What did you find? If you did like I did, then your calculator returned an answer of undefined. What's going on here? Well, let's see what's going on. Let's write out the numbers. The index of refraction of water is 1.33. The angle of incidence is 50 degrees. The index of refraction of air is 1.00. When you do the numbers, you find you're trying to take the arc sign of a number that's greater than 1. Since the sign of the angle can't be greater than 1, then your calculator tells you that you've made a mistake. Well, in fact, you haven't made a mistake. There's a physical interpretation about what's going on. And it's this. Instead of light crossing the boundary, the light gets totally reflected from the boundary back into the original material. This phenomenon is called total internal reflection, and it's exploited by many optical manufacturers to build a whole mess of practical optical devices, including binoculars and telescope eyepieces and periscopes and the like. To appreciate total internal reflection, let's do a Gedanken, which is German for a thought experiment. Suppose we took a submerged laser pointer and directed it upward onto the water-air interface. Now, don't try this at home or you'll ruin your laser pointer. Let's slowly alter the angle that the laser beam hits the boundary. What would we see? Well, we'd expect to see reflection and refraction happening at the boundary. And indeed, that is what we'd see. But if we're watching carefully, we notice something else too. We'd see that as we increase the angle of incidence, the refracted ray becomes less and less intense, and the reflected ray gets brighter and brighter. Then, at some magical angle, which we're going to call the critical angle, the refracted ray disappears altogether, and all the light gets reflected back into the water. The incident ray is totally reflected back into the incident medium. It gets totally internally reflected. So, what is this magical angle? We calculate it by setting the angle of refraction equal to 90 degrees. We define the critical angle to be the angle of incidence at which the angle of refraction would just equal 90 degrees. This critical angle is going to depend on the different materials that are at the interface. We're going to calculate a special one for water and air. We begin Snell's law, and then we say for the critical angle, theta water, the critical angle, is going to be occurring when theta air is equal to 90 degrees. When we make these substitutions, here's what we see. Since the sine of 90 degrees is equal to 1, then I can solve this equation for the critical angle. And it's this equation that results from a strategic application of Snell's law that I can use to figure out what the critical angle is going to be. I don't think this equation is worth memorizing. What I think is worth memorizing is the fact that the critical angle occurs when the refracted angle is worth 90 degrees. And you can solve for the expression for the critical angle if you know that. Let's figure it out for water. I find that for a water-air interface, the critical angle is 48.75 degrees. What this means is that if the angle of incidence is less than 48.75 degrees, then some light's going to cross the boundary into the air. But if the angle of incidence is greater than the critical angle, then all the light gets internally reflected. None of it will cross the boundary. Big deal. So what? Well, here's the big deal. If you design things just right, you can pipe all that light down an optical fiber. If you are in the telecommunications industry, then you can make money off of this. It's the principle on which optical fibers work. Total internal reflection. That's a big deal. The Electric Power Board of Chattanooga would love to sign you and your family up and supply you with a whole host of information through their new optical fiber network. Comcast doesn't like it because now the Electric Power Board is competing for the same customers. What is necessary for total internal reflection to happen? One important factor is that the incident medium must be more optically dense than the refracted medium, and you need to write that down. That's the only way that you're going to get this undefined arc sine function to appear. From a practical point of view for optical fibers, this means that the transparent fiber along which the signal is carried must be clad with some material that has a lower index of refraction, as shown in this diagram here. If we have an opportunity in class, then we'll take a laser and shine it into this sort of situation and see the light bounce through the material. It's a pretty cool thing to see. Let's work a numerical example. 63.1. The index of refraction for yellow sodium light in crown glass is 1.52. Find the critical angle for yellow sodium light entering air from crown glass. Okay, let's draw a picture. In this diagram we have crown glass on the top side, we have air on the bottom side. Crown glass happens to be something that is used. It has used in various optical instruments. It has a fairly high index of refraction. Now we want to find the critical angle. Remember, here's the important definition. The critical angle happens when I have a denser incident medium than I have refracted medium, which is the case here. The index of refraction of the crown glass is 1.52. The air has an index of refraction of 1. It happens when the angle of refraction is equal to 90 degrees. Let me sketch that in this diagram. So what that means is that the refracted ray would travel just along the surface of the interface. So we're going to find this critical angle now using Snell's law. Let me substitute the fact that theta glass is going to be the critical angle and theta air is 90 degrees. And we recognize that the sine of 90 degrees is equal to 1. So we can solve that equation for the critical angle. And now let's put in the numbers and figure out what the angle is. I get that the critical angle is just over 41 degrees. If the angle of incidence is greater than this 41 degrees, then what I'm going to find is that I get total internal reflection and nothing comes through the boundary. Now, let's take up dispersion.